Hello everyone. We already have started different consideration associated with capacitive sensors, and we have seen in the last lecture what are the different architectures or geometries that we may use for sensing applications. We have seen that one of the structure could be if we can use a structure where this dielectric material is movable. For certain application, we will see how to use it for a application. We briefly explained one application, and then we also have seen another architecture where, say, the material, this dielectric material is reactive, and then say after reaction it creates a different material. Then also you will find that the same capacitor can be used for a sensing application. Now, based on the geometry and architecture, one can actually divide the capacitive sensors in three different types, majorly in three different types. So, the first type is displacement capacitive structure or displacement capacitive sensor, where, as I have told, the displacement associated with this dielectric layer will actually give you an output which you can correlate with the physical quantity. The second type is overlapping area variation, where the overlapping area will be varied in presence of a stimuli, and then you can correlate the total capacitance with that stimuli. And then the third one is effective dielectric permittivity variation based capacitive sensor. So, in this case, the effective dielectric permittivity will change, and this change in effective dielectric permittivity will be correlated with the external stimuli. So, these three types basically comes from the definition of the capacitor. So, if you see, we have three different parameters that we can vary in a capacitor. The first one is the distance between the metal plates, and if we can vary the distance between the parallel plate capacitor between the parallel plates, then this will give you a change in capacitance, and then you can quantify the same. This is that displacement capacitive sensor. This is actually a displacement capacitive sensor. If you can vary the displacement, if you can vary the distance between two electrodes, so definitely you will get a response accordingly. Apart from that, if you can also displace the dielectric material, then it will create a combination of capacitor. This also is a kind of displacement capacitive sensor. And then if you vary the total cross sectional area, then you will get an overlapping area variation based capacitive sensor. And similarly, if your epsilon r, that is the dielectric permittivity, is changing, then also you will get a change in capacitance, and that also will act as a sensor. In that case, we can call it effective dielectric permittivity variation based capacitive sensor. So, briefly we have discussed the displacement capacitive sensor, but here I am showing a different geometry which is again based on displacement capacitive sensor. Say you have a substrate and you have created a bottom electrode and a top electrode. The top electrode is connected with a diaphragm. Now, the diaphragm is movable. So, if you press the diaphragm from top, this diaphragm will kind of bend. Okay. Now, if it bends, then definitely the distance between these two electrodes, top and bottom electrode, that is D, will vary. Now, if D varies, say if it is C epsilon 0 epsilon R A by D, then if D varies, definitely your capacitance will vary. Now, based on that capacitance, that you are getting in the output, you can quantify what is the applied pressure or applied force. So, force can be quantified using this type of sensor. You can call it a pressure sensor or force sensor. And in this case, if you see that the distance, the variation in distance is not uniform. For example, if you make a spring arrangement in these two sides, and if these plates are coming close to each other, keeping this distance constant throughout, then it's much easier, because anyways you can use this equation directly. You mean what I say? For example, say when the pressure is not there, this is the initial position of top electrode and bottom electrode. The moment you put pressure, the position will shift here, the top electrode will come here. So definitely, if the initial distance is d1 and final distance is d2, then your capacitance C1 is epsilon 0 epsilon r A divided by d1, C2 will be epsilon 0 epsilon r A divided by d2. But in this case, if these two junctions are not kind of a spring arrangement, you will find that the deflection is something like this. Wherever you are applying the pressure, it will bend like this, and the distance, this d2, will not be uniform throughout its length, throughout its cross section. Consider this room as a capacitor, where the floor is one metal electrode and the roof is another metal electrode. Now the side walls, if these side walls are spring, then if someone press from the top, that is if somebody press on the roof, then the entire roof will come closer to the floor, and then it's much easier. This is the case. The roof, entire roof will come down because your side walls are spring, kind of spring arrangement. But if the side walls are fixed, and if your roof is a kind of diaphragm which is deformable, and if somebody then press from the top, then the middle portion of your roof will come down. So you will find in the side view, you will find the roof is actually bending like this, right? So the distance here and here is not same. There is a variation in the distance. In such a situation, you have to calculate the total capacitance in that way. So one of the way to calculate the same is, consider this as a symmetric structure, because the deformation in the left side will be same as the deformation in the right side once you press from the top. And then let us consider this structure only. If we can calculate the capacitance of the right hand side, then we will multiply this with 2, then we will get the capacitance of the entire structure. We can take this approach in order to solve this problem. Say one side structure will be something like this after you apply the force, and this is your side wall, that is this part. Okay. Now here you have applied the force or pressure, so you will have a structure like this. And in order to solve this, what you can do is you can consider a small cross section, say dx, and then you figure out what is the variation of this distance with respect to x. Say this is x. You can approximate this variation is kind of linear. So you can approximate, say, the distance d, if this is the distance variable, then d, that is y equal to mx plus c, that is the linear consideration. Say here if it is d0, then c will be d0, m is the slope, x is the distance from here, and then y is your distance. Now if x is equal to 0, your d is equal to d0. So here x is 0, so your d is equal to d0. And then say for this part only, you calculate the capacitance, which is C is equal to epsilon 0 epsilon r A by D. So here it will be like epsilon 0 epsilon r. A is width into dx, because this will be your width. So width into dx, this is dx, will be your cross section, and then d is m into x plus d0. And then to figure out the total capacitance, you can integrate the same from 0 to, say, if the length is L, so 0 to L, and if you integrate the same, you will get the total capacitance. And based on the pressure, this deformation will take place. Here, remember, we have taken an approximation that this dependence of x with d is linear. If it is not linear, you take that approximation, and then the value of d0 will be a function of p, and then the value of m also will be a function of p, and then if you put those values, you will be able to theoretically measure what will be your total capacitance if you apply certain amount of pressure or if certain amount of force, right. So this is one way of fabricating a displacement capacitive sensor, and you will find this type of sensors are there. Secondly, in this case, one problem is if at certain pressure your top electrode touches the bottom electrode, then it will short the circuit. So in such a situation, it's better that you put a dielectric layer on top, and this dielectric layer will give you a capacitance value for maximum deflection, that is C0, and your sensor will not get shorted in any case. So this is a kind of arrangement that you can make just to make sure that both the electrodes are not getting shorted. So you can actually deposit a dielectric layer on top. Okay. So this is one type of displacement capacitive sensor. Another type of displacement capacitive sensor we already have seen. So in this case, what you have changed is the distance between two electrodes, top and bottom electrodes. But in this case, what you are changing is the effective capacitance of the entire structure. So this also can be considered as the effective dielectric permittivity variation based, because the effective dielectric permittivity of the entire structure in this situation is not same as epsilon 2. But again, because you are actually displacing this dielectric material in one direction or another direction, you can also consider this as a displacement type capacitive sensor. Now, if this is the situation, you know what is the total capacitance, and let us see how we can use this type of structure for an application. And for that purpose, we have taken example of water level monitoring. So in this case, what we are doing is we have taken an parallel plate capacitor, same as this one. What we have done is we have rotated the entire structure by 90 degree, and then this is how it looks. Previously it was horizontal, now it's vertical, and then we have put this sensor inside a water tank. So this is a portion of a big water tank. You have a very big water tank, you kept a capacitive sensor somewhere, and you want to see the change or you want to detect the level of the water in that tank, or say even if you can consider a small vial where you have this sensor placed. Now in such a situation, if you start pouring water, the dielectric material between these two electrodes will now change based on the level of the water or level of the fluid for that matter, right. And here the dielectric is, say, air. Okay, here also it is air. Okay, just because this portion is in between two electrodes, so I have taken a darker shade. but consider this is air, so the dielectric material in this portion is also air. Consider the level of fluid is LF and the level of air in this capacitor is LA. So the total length L will be LA plus LF. And in this case, again, you have two capacitors like this. So you have C1 and C2. In this case, your C2 is CF, that is capacitance or capacitor value in the fluid, or Ca is the capacitor value or the capacitance value in presence of air. So your Ct will be C1 plus C2, as we have seen in the previous discussion, which is nothing but Ca plus Cf. Now the value of Ca is epsilon 0, epsilon A. L into A is your length and then width W. So width of this capacitor for air as well as fluid is W, which is constant. So this is the equation for Ca. So from here you will find La is nothing but L minus Lf. So we have replaced La with L minus Lf. So you will have the equation which is shown over here. Similarly, the equation for Cf will be epsilon 0 epsilon f into Af. Now Af can be written as Lf into W. Lf is the length here, right? Now the total capacitance, just replace the value of Ca and Cf in this equation. You'll have this value. If you do some rearrangement of these parameters, you'll find this is the value of Ct, total capacitance. Now if the level of fluid increases, the total capacitance will change, because Ct is a function of Lf. Now based on this change, you will be able to understand what is the level of the fluid. If it is water, then what is the level of the water. So this is an application of an capacitive sensor, okay, and this is how you can calculate the values associated with the same. So similarly, you also can think of a displacement type capacitive sensor, where you have a mass. This is the side view of the sensor. You have a mass which is movable both upward and downward direction. You have a top electrode which is known as cap. You have a bottom electrode which is known as base. Now you have a capacitance between the mass and cap. You have a capacitance between the mass and base. So you have two capacitance associated with this structure. Now if the entire structure moves with an acceleration, say towards upward direction, then this mass will deflect towards downward direction. So the value of mass and base capacitance and the value of mass and cap capacitance both will change. Now if you can measure the values of these two capacitance, you will be able to quantify the acceleration value. So this is the concept that I am showing. In fact, you can figure out the equation associated with the same. It's not very difficult. Again, in this case, your d1 and d2, both the values will vary, right? And your total distance anyways is fixed, which is d. So one can very easily calculate the value of the mass cap capacitance and mass base capacitance, and based on that variation you can detect the acceleration of a certain say vehicle. If you connect this with a vehicle, then you can detect the acceleration of that vehicle. This is the top view of the sensor, where the mass is actually suspended. You have two beams, in fact 4 beams that is connected with that mass. Now this mass will move up and downward direction. Now based on that movement, the capacitance value will change, and if you can calculate those capacitance value, you can actually correlate the capacitance value with the acceleration. So that is why you can use this structure as an accelerometer. So this is a MEMS sensor, micro electromechanical system. We call it micro electromechanical system because there is a mechanical movement of a sensor geometry which leads to an electrical change in output. So that's why it's a micro electromechanical system. An entire structure, this structure can be in a micrometer domain, in a silicon chip. So that's why it's an MEMS type of sensor. Okay, I'm not going in details regarding the calculation of this two capacitance. You can do it if you wish to. It's not again very difficult. Okay. Now the next type of sensor that we have said is a overlapping area variation based capacitive sensor. So I have probably discussed a similar type previously where there were 4 plates and then you have a top electrode. These 4 electrodes are actually metal plates. Then you have a top electrode and in between there was a dielectric. If you move this top electrode in certain direction, the overlapping area will change, and based on that the C1, C2, C3, C4 value will change, and you can actually detect the force applied on the top electrode. So to make this same concept simpler, what we have done is, in this case we only have taken one capacitor structure. Again, it's in parallel plate capacitor. It has a bottom electrode and it has a top electrode. Then there is a dielectric, say epsilon r, a dielectric in the middle. The top electrode is kind of movable. Now if somebody applies a force in this direction, the top electrode will move in this direction, and then the overlapping area will change. So you will find there is a change in the overlapping area. This is your initial capacitor or initial capacitance. So the initial capacitance value is epsilon 0 epsilon r A0 divided by d. A0 is the initial overlapping area, which is nothing but L0 into W. W is the width and L0 is the length. So the cross sectional area is L0 into W. But once you apply a force, the top electrode actually shifts towards the direction of force, and in such a situation consider the overlapping length is L0f and width remains the same, that is W. So the area A0f will be L0f into W, and that's why the value Cf, that is the capacitance value when you apply a force F, will change. Now if you can detect this capacitance value, you will be able to quantify this force, right, because the displacement is a function of the applied force. Now this is a arrangement where the overlapping area variation is actually helping you to measure a physical quantity. In this case it's a force. So this can act as a force sensor. Okay. Now the other type is effective dielectric permittivity variation. So in this case, what we have discussed previously, if you can figure out a similar situation where the reaction will take place from the bottom and will slowly progress towards the top depending on a reaction, then this can act as a sensor, and the same can be calculated using this equation. Even if you find that there is a capacitor and the material, the dielectric material inside is reactive to material say A, and the dielectric constant of this material changes with the concentration of A that is reacting with this material. In that case also the total capacitance value, that is epsilon 0 epsilon r A divided by d, the total capacitance value will change because your epsilon r is changing based on the reaction, and hence you can actually quantify the concentration of say A. So this is an arrangement where effective dielectric permittivity variation is helping us to sense something, to detect or measure something. So in this case, we already have seen that if two materials are different, then the dielectric constant is epsilon 1 and epsilon 2. So this C1 and C2 is like connected in series. So total capacitance will be 1 by C1 plus 1 by C2 is equal to 1 by CT. CT is total capacitance, and then you'll get this expression. We already have seen this. So this is an arrangement where you will find effective dielectric permittivity is actually changing. Now there are three take-home messages from this lecture. The first one is capacitive sensors can be of various types. We have seen three different types based on the variation of different parameters, and all these capacitive sensors can detect certain physical or chemical parameter or any kind of stimuli. Then we have seen capacitance of different electrode arrangements can be used for sensing application. So if electrode arrangements are different, that also can be used for sensing applications. So just in this context, I would like to mention that there are capacitive sensor where people use interdigitated structure, and the capacitance between these two electrodes are used for detecting different chemical and physical parameters. So instead of only top and bottom electrode and just changing the distance between these two electrodes, what they do is they also create microstructures and then also vary the cross sectional area of these two structures and then calculate the total capacitance, and at times you will get higher sensitivity. So this is just a special case that I wanted to mention, but if you change the electrode arrangement, that also can be used for various sensing applications. And thirdly, electrodes of a capacitor can be engineered to fabricate a capacitive sensor. So you can also engineer the electrodes and then can fabricate a capacitive sensor. For example, if you can make it a movable electrode, then this will act as a kind of, say, force sensor, as we have also explained in the previous slide maybe. So this is these are the different types of sensors that one can make. So in the next or upcoming discussion, we'll see details associated with thermal sensors and temperature sensor. Till then, thank you.